pursue next year. And I'll also mention the new postdocs at the DHI at that reception. So there will be a bus leaving from the Center for Astrophysics at around 11:50. And you can sign up with Mark Palmer at the ITC. Okay, and other than that, Martin is off to a good start with the Philosophy Forum. It looks like there were two excellent sessions. The latest one, thanks to Jeremy. The reading material was fascinating. Lots of things to think about. Would you define the outcome as a success?
Yes, so far definitely.
Are you wiser today than you were yesterday, before the meeting?
I hope so.
That's the way you should measure things. Every morning when you wake up, are you wiser than you were yesterday? So far my answer to myself is yes. I've never gone, but of course you would never recognize if you lose intellectual ability at some point. Okay, 2 talks. Who is presenting?
Go ahead. So we are very lucky to have Jeremy Butterfield from Cambridge talking us about deriving time evolution, general relativity, philosopher's viewpoint. He's actually with joint work with Enrique Gomez, who's here also. So in the questions, I'm sure all your questions will be answered. We have 2 experts.
Okay, well thank you so much, RB and Martin, and indeed BHI generally. Great pleasure to be here. Some of you heard a preamble to this yesterday morning, but my memory is that we have half an hour, and including discussion. And I think it's true that in order to operate this thing, I should simply go like this. Yeah, correct. Fine, thank you. So I'll try and talk for 20 minutes. You probably know the joke about the chauffeur who knows all the answers. Enrique is the real brains of this. You may remember primary school, early September, you had to do a book report on what you'd read during the summer. This is like Jeremy's book report on deriving time evolution in general relativity. But there are the topic broadly coming from philosophy is that there's this thing called functionalism, which is roughly proving that some entity or concept is the unique satisfier of some long description, which is scientifically interesting to know that it is the unique satisfier. And the emphasis here is the interplay between the physics of matter and the physics of geometry, especially as regards the evolution over time. And there are 3 things of which I'll try and spend 6 minutes on each. There is a classic paper, HKT of 76, called Geometrodynamics Regained. There is a less known series of papers by largely German authors, Duhlschuler, Giesel and others, 2012-2018 in Physical Review D. And all this is leading up to Enrique's work of some 3 years ago with Shyam. Also, they were then both at Perimeter Institute. They are all about showing roughly that the ADM Hamiltonian is the unique satisfier of a certain natural condition you might wish to write down, or rather, it's a certain condition that you might consider natural, if you are sufficiently wise, as Arvid was emphasizing. So that's the topic, and in reduction, as we say in philosophy, you've got a problematic discourse or theory which is in some way legitimized by being shown to be part of something you considered unproblematic, and this is done by showing that each of the problematic concepts, there could be more than one, but is in some way uniquely filling a description that you extract, that you write down in terms of the unproblematic discourse. So this was gone into detailed philosophy angle yesterday morning.
But it's also useful for politics.
Yeah, right. So we are interested in functionalism about time. So the idea is temporal concepts are going to be located in this kind of landscape of ideas that we, in particular the temporal metric, is going to be located in a landscape of ideas that we find unproblematic. So all 3 enterprises will be involved with a Lorentzian metric, and they will be involved with the ADM Hamiltonian of the Arnovit, Desa, Misner, early 1960s extraction from the Einstein field equations of a canonical 3+1 way of thinking of general relativity with time evolution generated by this Hamiltonian. And it's written there, they either assume or deduce, and they focus on. Those vague words are because actually the exact achievement of the three programs is very different. But we're going to deal with them in what we might call chronological order, and it's true that the first one, Heumann, Kukash, Teitelbaum, is used in the later two. Okay? And so there are going to just be three sections, and indeed, although it says at the bottom a horribly high number of 27 slides, we're not going to pause on most of those. They're just there to make me feel they're like a security blanket, you know. In Peanut, Schroeder has a security blanket. I have my security blanket. So anyway, this is HKT in 1976. They do assume a Lorentzian manifold, but they say let us foliate it into space-like surfaces. So there is a kind of given three-dimensional spatial manifold sigma, which gets embedded, and this is the map of the embedding with a point little sigma in the fiducial manifold big sigma, gets embedded at different times, and an arbitrary vector field in the four manifold big M is resolved into lapse and shift components using the Lorentzian metric. So, what do? Well, they say, let us consider the way the embeddings mesh those various slices. Let us talk about infinitesimal deformations of a slice into another slice, and think about the algebraic structure of those deformations using Lie derivatives and Lie brackets. And then let us announce that we wish to have a Hamiltonian framework which mirrors that algebra. Then, ... many pages later, the ADM Hamiltonian is the unique satisfier of the constraints we have announced. So a philosopher would say, they have shown that the ADM Hamiltonian is the unique occupant of a functional role, namely generating how spatial geometry changes over time in a way that reflects the deformation algebra. So here are some details, but like I say, I'm not going to pause. That is a glimpse from Teitelbaum 1973 of the interaction of the per versus parallel contrast, lapse and shift, interacting with the Lie bracket for the vector fields on the four manifold. So this is the deformation algebra about, deform it one way, deform it a second way. Now imagine doing those things in the reverse order and comparing the results. That's the Lie commutator. Sorry, I should have said this. At the bottom there, in italic, the main idea, you've written down a deformation algebra and now require that it be emulated by the constraint algebra of a Hamiltonian theory. And this is the kind of thing they then write down, which if you're familiar with Hamiltonian approaches to field theories, you see smearing functions psi, you see Poisson brackets, and the equation 5 contains the main claim, require that this thing reproduces a deformation algebra. The shift is hypothesized to be the usual generator of spatial diffeomorphisms, and there is a requirement, equation 7, that the scalar constraint which will do time evolution must be related to the extrinsic curvature. So again, there's an appeal to a Lorentzian metric there, and that is motivated, but it is an appeal to the pre-existing Lorentzian metric. But yes, there you get it. Actually, the ADM Hamiltonian is the only thing the scalar constraint could be. And this achievement, much cited, is used later by, in particular, the German school. There's philosophy reasons why we would be interested in the German school, which we'll come to. But the main physics announcement is that there is a manifold, a four manifold that is assumed, but it is not assumed to have a Lorentzian metric. It's just a four manifold. You assume that there will be matter and radiation in this manifold, and it will be subject to an action function which is diffeomorphism invariant, and it will be subject to other requirements about there needs to be an initial value problem, there needs to be a difference between positive and negative energy. Given just that, quite heavy invocation of what I was joking with Enrique I would call Courant and Hilbert Volume 2 on PDEs, right? Causal cones, characteristic curves, and so on. There is a sort of the extraction of a causal cone structure and the idea of a space-like surface as a surface which is never tangent to any of these causal cones, but there still isn't a Lorentzian metric. And you haven't said anything about the details of matter. You've just got an arbitrary large tensor of unknown valence, capital A, right, which could have any valence. But you know something about the evolution of this geometric structure and the matter, and they then adopt in more detail a 3+1 perspective. They plug into HKT-like technology, and they prove that for what they call standard model matter, but it really means classical matter, electromagnetism and spinors, the implied space-time geometry has a Lorentzian metric, and it's the ADM Hamiltonian again that controls the evolution of spatial geometry in the 3+1 picture of that Lorentzian metric. So this is quite remarkable. As they stress in their opening pages of their papers, it is partly that they're interested in the systematic exploration of rivals or alternatives to general relativity. Admittedly, their systematic exploration is confined to the conditions we had before. There has to be some assumption that there is some or other action functional, and also these conceptual requirements of what they call being well behaved and predictive, which is things like having an initial value problem. So it's also true that their papers don't actually exhibit in detail the recovery of how this goes with exotic modes of matter. But it is, as I said, interesting to philosophers because there is a much beloved New Zealander, American, Harvey Brown, a philosopher at Oxford, now just recently retired, who wrote a book called Dynamical Relativity some 12 years ago. It's about what he calls the dynamical approach to space-time theories, which is about understanding in detail how it is that our instruments read off, as we put it, the metric tensor. So this kind of inquiry in the foundations of space-time about putting the matter back into the space-time geometry thinking is, well, it's a well-respected tradition, especially in that little island off the northwest coast of Europe they call the United Kingdom. Okay, won't go into that joke any further. Time.
Will not exist for that much longer.
And there are wonderful details. I find that I have not actually understood their paper, and it's a complex collection of ideas. And let me move to my third case study. So, Enrique and his co-author Shyam, they don't assume a manifold. So in a way, we've been getting better and better results by less and less assumptions. We began with a Lorentzian manifold, then we had a manifold that needn't be Lorentzian. Now we don't start with a four manifold. We start with a three geometry. We certainly don't, and particularly we don't have a diffeomorphism invariant action functional being assumed. This spatial geometry of this three manifold is required to vary over time, and this variation over time is to be in a certain sense locally definable. With some heavy lifting and long calculations, it is possible to prove that there is a four-dimensional space-time with a Lorentzian metric, and that the geometry is evolving over time by the ADM Hamiltonian. And I wrote down in A the chief technical imposition, that the variation over time is to have at most second order dependence in the variables. I call them momenta. They are announced as being the conjugate variables of the spatial geometry. So it is an avowedly and explicitly, so this is an assumption, Hamiltonian framework enterprise. So the details go a bit like this. We'll stay with this for a minute. Main thing is the first 4 lines. It's like an opposite direction of travel to that much honoured and rightly admired HKT paper. HKTs start with the Lorentzian manifold and they move to a Hamiltonian framework and then prove the ADM Hamiltonian is unique. GS impose a Hamiltonian framework on 3 space and they get to a Lorentzian space-time. But in both cases there's a unique characterization of the ADM Hamiltonian. So, what does it mean to impose a Hamiltonian framework on 3 space? Well, capital B, and so on. Capital A, you've got a localness of the generation of change with a kind of independent evolution of what happens in disjoint spatial regions. That's equation 11, a Poisson bracket in Spanish. And there is a kind of equation 12 there about the standard generator for diffeomorphisms and a reminiscence of HKT. There is, again, completely arbitrary shape initially to the scalar Hamiltonian, except that it's the sum of a kinetic and a potential term, and the kinetic term must be at most second order in momenta, and the ADM Hamiltonian is deduced. Okay, final slide. A philosophical payoff here is that, okay, I'm from Cambridge, so we've got this guy Bertrand Russell. He was a good stylist, he made a lot of good one-liners. One of them is, you shouldn't just postulate what you want, you should deduce it. And, in particular, you should deduce it because that's the honest thing to do. Just postulating it is theft. And he said, I do honest toil, I don't do theft. There is a noble tradition, you may have heard of it, it's called shape dynamics. It's very 3+1. Enrique worked in it many years, wonderful things that he and his co-authors wrote. When you first meet it, it seems to write down the ADM Hamiltonian as a wizardly thing to postulate. And you might say, oh, naughty, you stole that from 40 years ago, ADM. Well, historical happenstance, yeah, maybe like they did, because they had read ADM, because they're good scholars. But intellectually, look, this GS result is telling you there's nothing thieving about it. From a shape dynamics type kind of point of view, it is entirely legit. Okay, so this was what I was talking about, and I am very, very grateful. As always, the main message in the bigger font. Thank you so much.
Do you have any questions?
So I guess the reason this is even more significant is because Hamiltonian formulations are fundamental to quantum mechanics, right? So once you have that step established, then you can start to think about how to quantize space-time.
Yeah.
But in the classical context, of course, there is one pathology, which is the Big Bang. I mean, you have ordinary matter, you go back in time, and there is a point in time when you can't go back anymore.
Yes. Yes.
That's what quantum mechanics
exactly. There's a deep thing here. I mean, from every point of view, historical, conceptual, mathematical. Of course, Dirac first tried to Hamiltonianize general relativity in the precursor years before ADM of 1960 for this reason, in order to quantify. And so this is certainly, I'll be honest, for me, I'm simply trying to do a little philosophical contribution to the foundations of local classical physics in this talk. But yes, it does have this much wider resonance, and it has a much wider limitation that actually, space-time isn't globally hyperbolic. Right? So this whole sigma times the real line structure that I've clearly had in mind is questionable. But Enrique, would you like to comment on the question?
Well, I don't know. I think the most adapted formalism to try to approach these questions in this formalism is to use something like Hartle-Hawking. That's more adapted to the 3+1. You can think of path integrals in configuration space with a certain initial condition. But yeah, I haven't thought about how to adapt the generation of this Hamiltonian, these constraints to that setting. But there's a paper by Hartle and Halliwell that is something that goes in this direction goes in the direction of HKT at least. So maybe there is something.
Yeah, I mean, other approaches, of course, are like inflation, that argues that once you go to the quantum level, that there are no initials. I mean, everything that can happen happens. Some parts of the universe are the ones we live in.
Right.
But,
Yeah.
So it does
Yeah.
touch on philosophy.
Yeah, right, sure does. I
The
mean,
approach.
capital P, philosophy of capital C, cosmology. Yeah, that's right. Yes, so I agree totally. There's massive issues there, massive issues.
Please.
I have a basic confusion about something you said in your talk. You said you derive a Lorentzian manifold merely by demanding Hamiltonian evolution of a three manifold. What do you mean by that? I can think of it bubble salt, and I can describe it in Hamiltonian dynamics. It will not lead to a Lorentzian three manifold. So, I mean, how do you derive the signature just from demanding Hamiltonian evolution? I don't understand that.
Well, you assume a three-dimensional Riemannian geometry. So, but you're right. No, the signature is not the right.
The signature is an additional input.
You derive it up to a signature.
Okay.
Yes, so in this sense, in fact, presentations of HKT often can be done with
Right.
just keeping track of whether you're Euclidean or Lorentzian too.
Right.
That deformation algebra can be written down with a minus or a plus in certain terms, reflecting whether you adopt it.
There was an epsilon in your formula.
Indeed. Did I have the epsilon
Yeah.
even? Yeah, which is plus or minus 1.
I had a question.
Yeah.
Are you familiar with Lovelock's theorem and other theorems like that kind of constrain the type of field equations you can have on the basis of symmetry, on the basis of what kind of
Yes.
order in derivatives you're allowed to put into your field equations? So I was wondering, these are trying to get at the same kind of thing, although not exactly the same, of course, but these are trying to constrain GR as a kind of unique occupant of some functional role.
Yes.
So I'm just wondering what you think about that.
Well, I mean, actually, I never read Lovelock's paper, but I've heard about it, of course, and Enrique and I were discussing. I mean, the main thing is it is confined to metric variables, and the second program is explicitly open to not having a metric. It's true that it settles down in the middle of their long paper into standard matter and then extracts a Lorentzian metric. But there is a way in which their scope is wider. And I didn't know this, but there is this area gravity program in which one of the authors, Schuller, is a proponent, in which, roughly speaking, the gravitational variable is a contractor of areas, not lengths, not vectors. And I don't know, Enrique, whether you want to add to this about Lovelock's theorem, even in the context of your own, like the GS, I just spoke about the Schuller-Duhl.
Right. No, I mean, I would only add that, Lovelock's theorem is, the difference is that Lovelock's theorem already assumes diffeomorphism invariance in a way, right? It assumes a space-time, or at least some version of the Bianchi identities. And this is, I think the appeal of this other theorem is that you don't necessarily need to start with space-time. If you have some spatial geometry and you have some consistency conditions about how evolution would work, you get the ADM, or you get basically Einstein space. So it's very restricted, even if you don't think about space-time itself. if you have a space-centric approach to
But maybe if you relax the demand that, like,
yeah, second momentum.
Second order.
Right,
momentum.
but also Lovelock's, right? Lovelock's
Yeah.
theorem also has similar restrictions, up to two second derivatives of the metric and so on.
Yeah, there needs to be a decoupling between the matter variables and the little g. So the second order equations for little g must depend on the first order equations for phi, some matter tensor fields, and vice versa, in fact. So that's one of the assumptions.
Right.
So there's an enforced decoupling there.
Right. Here, I don't know. To be honest, we did it for vacuum, so we didn't couple matter. But the assumption of second order momenta is still very broad. So you can couple the two momenta using Ricci's or covariant derivatives or whatever function of the metric you want, tensor valuing function, so that you contract the two momenta. But it's very, very general, and so is the potential term. So in a certain sense, it's also very broad, but there's certain assumptions. Yes, particular. There are ways you can justify second order momenta if you demand that the theory has a Lagrangian formulation as well, a Hamiltonian Lagrange formulation, and then you can appeal to something like Ostrogatsky's theorem, or even to just say it has also Lagrangian formulation, well-posed Lagrangian formulation, etc. That would already limit this particular type of thing too. Anyways, it's we limited it to two momenta and didn't talk too much about that.
Are there any other questions for the speaker? All right, then I guess we.
Oh, that's all right. I'm going to move this over here.
I don't know how to transfer that to your slides, I'm afraid.
No worries.
That is beyond me. I'm leaving for time. Yeah, never mind.
No, you're perfect.
It's okay for time. Yes. I'll go here.
Okay, so the second speaker for today is Dr. Vivienne Baldassare. I hope that the pronunciation is not too Italian for the last name. I usually do that.
Perfect.
Well, it's a very good last name for Italians. So Vivienne is an Einstein Fellow at Yale University, and she's an expert observer of black hole, and she actually discovered, among many other things, the smallest supermassive black hole a few years ago, about 50,000 solar masses. And today she will be talking about searching for active galactic nuclei in low mass galaxies with optical photometric variability.
Okay, thank you very much for having me. I've really enjoyed my time here so far. I know not everybody here is an astronomer or an observational astronomer, so please, if there's anything that isn't clear or that I haven't realized is very field specific, don't hesitate to ask me. All right, start with a little pandering over there. Supermassive black holes are ubiquitous in the cores of massive galaxies. So when I talk about massive galaxies, I'm talking about galaxies that have stellar masses, so the mass in stars, roughly greater than or equal to that of our Milky Way galaxy. And every nearby massive galaxy that we have looked at, we have found a central supermassive black hole. So beautiful HT picture from the center of M87, which is a giant elliptical galaxy, and M87 has a black hole weighing 6 billion times the mass of our sun. The Milky Way galaxy has a black hole much smaller, 4 million solar masses. And then when we get to little galaxies, we actually don't know very much about the population of massive black holes in these objects. So this is a picture of the Large Magellanic Cloud, which is a dwarf galaxy in our local group, and it has just a few percent of the stars that the Milky Way does. So its stellar mass is just a few percent that of our Milky Way. And we don't know whether it has a black hole, and indeed this is the case for most of the dwarf galaxies that we look at in our universe, even though dwarf galaxies vastly outnumber bigger galaxies like M87 or our Milky Way. And for these massive galaxies, typically how we find black holes is by detecting the influence that the supermassive black hole has on the stars or the gas around it. And so I'm very interested in finding black holes in these little galaxies, like the Large Magellanic Cloud. Okay, this is a very simplified schematic of different possible ways that we can form supermassive black holes. So we don't know how supermassive black holes are formed, but we have a few ideas. So one is that supermassive black holes start out when very massive stars in the early universe die. So a population 3 star in the very early universe would go supernova and leave behind a 100 solar mass black hole, which would then grow into the very supermassive black holes that we see in today's universe. You could also have a process where you have the direct collapse of a very massive cloud of gas, which would leave behind a larger supermassive black hole seed, maybe 10 to the 4 or 10 to the 5 solar masses. Or you could have some process which occurs in maybe a dense star cluster, such as a runaway tidal capture process, which would leave behind a black hole seed which was in between these. And depending on how it forms, the black hole has to do either maybe a lot of growing to reach the masses that we see today, or not so much if they form through a scenario which leaves behind a 10 to the 4 or 5 solar mass seed. So these processes would occur in the early universe. And the reason that we're interested in little galaxies is because the fraction of little galaxies at the present day which contain supermassive black holes is expected to be sensitive to the dominant way in which black holes form in the very early universe. So this is a simplification, but what's shown here on the y-axis is the fraction of galaxies that contain black holes, and then on the x-axis is the galaxy's stellar mass. So here is about 10 to the 10, 10 to the 9 solar masses, so that's roughly the mass of the Large Magellanic Cloud that I showed earlier. And the key takeaway from this is that for massive galaxies, galaxies which weigh more than about 10 to the 10 solar masses in stars, no matter how supermassive black holes formed in the early universe, basically every galaxy will have one. Where we see differences are for these dwarf galaxies, so around 10 to the 9 solar masses, depending on whether black holes formed via this stellar death pathway, leaving behind small black hole seeds, or this direct collapse pathway, which would leave behind more massive black hole seeds, the fraction of galaxies that has a black hole is different. So stellar death, more galaxies in this low galaxy mass regime will have a black hole, versus direct collapse where maybe about half of them will end up with a central black hole.
There is another effect that comes into play, which is kicks that black holes get when they merge. During galaxy mergers, the gravitational wave recoil would in small galaxies would kick the black hole remnant out of the host galaxy altogether. So then, irrespective of where it started, you will not have anything.
Right. So this is definitely a simplified picture of this, but the point I'm trying to make is that by studying black holes at the centers of these little galaxies, and particularly measuring their masses, we can potentially learn something about how they form.
Let's assume that there can only be at most one supermassive black hole in the galaxy at any given time.
Well, we know that there are galaxies that contain 2.
But they don't count towards the fraction, like you don't double, you don't count them as.
Right. So this, okay, so black holes and low mass galaxies are also expected to have masses that are similar to the mass that they formed at. So this is irrespective of whether they get kicked out or not.
How many of these galaxies with more than one supermassive black hole we know? How many percentage of them?
The percentage would be very low, but I can't give you a number off the top of my head, but these are referred to as like dual AGN. There are a lot of galaxy merger systems where you see two active galactic nuclei, so two supermassive black holes that are eating a lot.
It's possible that all quasars are basically fueled as a result of mergers, and then you have every quasar has a companion, but at large separation. It's quite possible. This is not ruled out.
But they couldn't have just formed in situ, just having different collapses occur, just slightly offset from the center of the total galaxy.
No,
You'd have to.
Because you see them at, I mean, the dual AGNs are at few kiloparsec separation.
Okay.
Yeah,
it's clearly
that's right.
a merger of them.
Yeah. People are very interested in finding ones that are much closer together, but it's difficult. Okay, so if we can find black holes in dwarf galaxies today and measure the black hole mass, we can maybe say something about how big it was when it initially formed. So this is just a histogram from some recent work which simulated a sample of about 50 or so dwarf galaxies, and what's shown here is the fraction of the total black hole mass that is accreted versus how much it was born with. And so most of the galaxies in those simulations, their black holes didn't grow very much, and you have a handful where it maybe accreted 5 or 10% of its total mass. What's shown here is another simulation, which is looking at the black hole mass versus the bulge mass of the galaxy. And the point here is that the black holes don't grow very much until the galaxy exceeds a certain stellar mass. So if you're looking at smaller galaxies, then they might have black holes that are similar in mass to when they formed in the earlier universe. Okay, so we very much want to find black holes in small galaxies because they can teach us about black hole formation and growth over cosmic time. But unfortunately, black holes in small galaxies are relatively small, and thus finding them is really difficult. So when we look for black holes in bigger galaxies, so these supermassive black holes that are maybe 1 billion times the mass of the sun, it's very easy to detect the influence of that black hole on the stars around it. For these smaller black holes, the ones we're looking at are maybe 100,000 times the mass of the sun. We really can't detect that except for the most nearby systems. So what we do instead is look for black holes in small galaxies that are active, so eating a lot of material, and the material around the black hole is very dense and emits a lot of radiation. So this is what we refer to as active galactic nuclei. So we're searching for active galactic nuclei, or AGN, in low mass galaxies. Until very recently, there were just a handful of dwarf galaxies that were known to contain AGN. So this is a quote from a paper in 2004. So just 15 years ago, there were only 2 dwarf galaxies that were known to have AGN, and these were serendipitous discoveries.
Sorry, is there like a specific threshold luminosity to define something as an AGN, or what?
There's no standard definition, but you can talk about it in terms of the Eddington fraction. So maybe above 10 to the minus 2 Eddington could be an AGN.
Sagittarius A star is not.
Yeah, right. So Sagittarius A star is accreting at 10 to the minus 8 of its Eddington luminosity. So it's very inactive. So here we're talking about things that are accreting at tenths of a % of their Eddington fraction. Yeah, there's no standard definition in it.
Wait, 10 to the minus 2 or 10 to the minus 10 to the percent is 10 to the minus 3.
Yeah, like I said, there's no
Okay,
exact
okay.
threshold. It sort of depends on what we what our detection capabilities are here, if it's active enough for us to see.
Okay.
Okay, so in the last 15 years, this field has really exploded thanks to the existence of many large-scale surveys, like the Sloan Digital Sky Survey, where observations have been taken of tens of thousands of galaxies and have enabled us to search for these AGN signatures in very large samples of dwarf galaxies. So I've done work in a lot of these areas, but today I'm specifically going to focus on searching for AGN and dwarf galaxies using optical photometric variability, which is looking for changes in the light output from the AGN over years-long timescales. Okay, so I'll just say a few words about what has traditionally been the most successful way of finding AGN and dwarf galaxies, which is optical spectroscopy. So when you look at the optical spectrum of an AGN, you have emission lines, and these are produced in gas that is photoionized by the accretion disk around the black hole. If you measure the relative strengths of these emission lines, you can plot your object on what is known as the BPT diagram. So this is just showing the ratios of different emission lines. And depending on whether the galaxy falls up here or down here, you can say something about the photoionizing spectrum. And galaxies that have AGN tend to fall up here where these red and purple points are, whereas galaxies where the gas is photoionized by star formation primarily tend to fall down here. So generally speaking, galaxies in this region are star forming, and galaxies up here have active galactic nuclei. And so this was a work that looked at 25,000 dwarf galaxies and measured their emission line ratios, and they found about 130 of them that had signatures of an AGN in their optical spectroscopy. And so that might not sound like a lot, 130 out of 25,000, but that alone represented an order of magnitude increase in the number of dwarf galaxies known to contain AGN. So this technique can find AGN in low-mass galaxies, but there are limitations. So this is showing the same x and y axis as this same type diagram. But what's shown in these tracks are if you change the metallicity of the galaxy. So these ones reflect galaxies that have high metallicity, whereas galaxies with low metallicity are over here. And the takeaway here is that if you have a galaxy that has low metallicity, even if it has an AGN, it will not fall in the AGN region of this diagram. And for low mass galaxies, these are more likely to be low metallicity systems, so this effect is important. And low mass galaxies tend to have a lot more star formation, and this could dilute the signal from an AGN so that you don't detect the signature of the AGN in its narrow emission lines. So if we're only searching for AGN in low mass galaxies using this optical spectroscopic technique, then we're probably missing a significant population of them.
I was just curious that it's 1 year before he was elected.
You know, big career change. Real Renaissance man.
Yeah, sorry. Do you have any intuition why for lower metallicities they are going out of the band?
Why this happens?
Yeah.
So this is plotting the ratio of nitrogen to hydrogen, and in astronomy we consider nitrogen to be a metal. So basically there's just less metals in the galaxy, lower metallicity. So the ratio decreases. The ratio of nitrogen relative to hydrogen will decrease.
And these are like stoning gun for having AGN, right? Do you have can you have some AGNs that is not like launched by these metals or?
It's not that the AGN is launched by it in any way. It's just has to do with the gas that's in the galaxy. So what gas is available to be photoionized by the photons coming from the AGN accretion disk?
And by the way, all quasars, all AGN show very high metallicities in their vicinity, the broad lines. All of them. So it's like a few times the solar metallicity. But far away, where the galaxy is not affected so much by quasar, the metallicity can be low.
Okay, so now I'm going to talk about optical photometric variability and using this to find AGN in low mass galaxies. So it's been well established that AGN basically vary at any wavelength that we observe them on a wide variety of timescales. This variability tends to be aperiodic and the amplitude can change over time. And this is typically attributed to some instabilities in the AGN accretion disk. So this is just one example. This spans about 10 years or so of a well-studied AGN. And this is an optical wavelength, and this is just showing how the light output from the AGN changes pretty drastically over time.
Is there any periodicity associated with this? Or?
No, not usually. There have been, so it's not that maybe some of these dual AGN systems could show periodic variability, but generally it's aperiodic. Yes?
And you said this changes in several wavelengths for a given AGN. Do the changes in one wavelength correspond to another wavelength? Even if they're aperiodic in one wavelength, do you see the different wavelengths moving together?
So generally, there tends to be more variability at shorter wavelengths, so the amplitude is higher. You do see them vary together, and sometimes you can see that variability reflected in gas that is farther out, so you'll see variability from a region that's closer in, and then you'll see it some time lag later from a region that's farther out. And this has been a very prolific way of detecting very massive quasars looking for photometric variability, and so I want to use this to find AGNs in low mass galaxies. Okay, so to do this is complicated because we're looking for a relatively less luminous AGN, which is superimposed on top of its host galaxy. So what I do is use a difference imaging photometry approach where we're basically subtracting off the light from the host galaxy to try to detect any variable AGN underneath. So I'll just walk through some of the basic steps here. You construct a high quality template image from your best images, your best frames, so these have the best seeing and the lowest background noise to make your high quality template. And then what you do is you take each individual exposure and you basically degrade your template image to match the resolution of that individual exposure. And then you subtract off the template, and what you're left behind with is this relatively flat image, and if there's anything variable, it should pop out against the background. Okay. And then from there, I construct a light curve, so the light output over time, by putting down an aperture over the center of the galaxy and measuring the difference image and the template. And so then your final point on the light curve is just the template plus the difference image. So this is a galaxy that is not variable. So the black points here are the measurements of the light output, and then the blue line is trying to fit a model for AGN variability to this galaxy. But this object is not variable.
What's the mass of this galaxy?
This one I don't remember. It was just for an example of one that is not variable. So, yeah. And then for galaxies that are variable, we determine if that variability is AGN-like by determining how well it is fit by a damped random walk model. So a damped random walk has been found to be a good empirical descriptor of AGN-like variability. So this is something that behaves like a random walk on short time scales, but achieves a finite variability amplitude on longer time scales. So this is an example of a galaxy that is variable. So you can clearly see the variable AGN and the difference images there. And I think this galaxy has a stellar mass of a few times 10 to the 9 solar masses, maybe 5 times 10 to the 9.
What's the fraction of the flux in the variable part? I mean, with respect to the total flux of the galaxy.
Yeah, for this one, maybe like 10%, but it can be small.
So when you model it with like a random walk, is this random walk in time or in a space?
In time.
Yeah, but then don't you, I mean, if you look at this for a very long time, could it be that AGN just, get out of the cover, or it's a bit like transient to imagine that it's gonna to be random walk forever, right?
Sorry, what was the?
I want to know, is there any because random walk doesn't have any time direction.
This is a damped random walk.
Okay.
And it has 2 parameters, one which is a characteristic variability timescale, and the other which is a variability amplitude. So basically you have some perturbation, some random perturbation, and then there's a characteristic timescale on which that damps. Does that make sense?
Yeah. But afterward it's just damped away. That was
Well,
my
you can
kind of
have
intuition.
You have perturbations that continue to occur.
It's a bit
In the
like
accretion
getting
disk.
gradually sober. The drunk man is randomly walking on a line.
Yeah.
As time goes on, he gets more sober, so or at least more stationary, tired, so he jumps less often, right?
Actually, my favorite description of the damped random walk is exactly that. It's like a drunk person, but who always makes it home at the end of the night.
The right home move line. That's the difference, right?
Right. Okay. Okay, so the first sample that I did this analysis for was the SDSS Stripe 82 sample, which took repeated images of galaxies between 2000 and 2008. And I looked at 28,000 galaxies that were in this region of the sky, and they all had stellar mass estimates and measured distances. And so these galaxies, the total sample ranged in stellar mass from about 10 to the 7 to 10 to the 12 solar masses. And of these, I found 135 that had AGN-like variability. So this is just showing the histogram of the parent sample in gray, and then the variable AGN in orange. So they skew towards higher galaxy stellar masses, which you might expect.
Sorry. The time and scale of variability has also something to do with meteoricity and mass of galaxy, or?
No. It doesn't. There's
So what
been
does
some question.
What does control it then?
The timescale? It's not clear. There's been some question as to whether the timescale of variability is related to the black hole mass, which is something that I've started to explore, but at least for the black holes that we've been looking at, I haven't seen any relation between the variability timescale and the black hole mass. So it's not clear what sets the timescale. Okay, so because all of the galaxies in our sample had spectra, we were able to look at where these systems fall on this diagram. So this is just the diagram that I showed earlier that allows you to separate galaxies out into having narrow lines that are AGN-like or star formation-like. And so what I found was that for very massive galaxies, so the points here are color-coded by galaxy stellar mass. Yellow is very high stellar mass, purple is low stellar mass. And for galaxies that had high stellar masses, everything that had AGN-like variability, for the most part, also had narrow emission lines that were consistent with the presence of an AGN. for low galaxy stellar masses, so for small galaxies that we're interested in, about half of the galaxies that had AGN-like variability fell in this star formation dominated region of the diagram. So what this tells me is that the variability selected AGN that have these star formation dominated narrow emission lines could be AGN that are missed by other selection techniques due to the effects that I talked about earlier. So I've recently been carrying out an expanded search for variability selected AGN using the Palomar Transient Factory, which covers almost the entire northern sky compared to Stripe 82, which covers about 275 square degrees. And here we had about 30,000 low mass galaxies in our sample, compared to about 5,000 in the Stripe 82 sample. I realize I'm running low on time. So these are just a couple of examples from the Palomar Transient Factory of galaxies that have AGN-like variability and are low mass. So the blue line here is the best fit damped random walk model, and the shaded region are just the model uncertainties. And again, the gray points here are the measured nuclear luminosities for each galaxy. So these galaxies are relatively low mass and show AGN-like variability. We find something very similar to with the Stripe 82 survey, which is that galaxies at low stellar masses tend to have narrow emission lines that are dominated by star formation. This is the last thing I want to touch on, but we look at the variable AGN fraction as a function of the galaxy stellar mass. So the numbers here just show how many galaxies there are in each stellar mass bin. The red shaded region just shows where we are incomplete in stellar mass. So we basically looked at every galaxy below about 2 times 10 to the 10 solar masses, and then a smaller sample of more massive galaxies. So this is showing the histogram of the stellar mass distribution for the full parent sample in gray, and then the variable AGN in blue there. But we can't take the drop in the variable AGN fraction towards low stellar masses at face value, because we also see that the variable AGN fraction that we detect declines as we move towards fainter galaxies. So this is the galaxy nucleus magnitude. So these are fainter, these are brighter, and basically it's easier to detect a variable AGN in the brighter nuclei than the fainter ones. So there's some question as to whether this drop-off is just a function of the fact that lower mass galaxies are fainter. So I compared the variable AGN fraction in magnitude matched samples of galaxies. So here is just a histogram of the galaxy nucleus magnitude. The gray is high mass galaxies above 10 to the 10. The pink here is the sample of galaxies between 10 to the 9 and 10 to the 10 solar masses. And basically what we do is draw weighted subsamples so that the magnitude distribution matches that of the higher mass galaxies, and then compare the fraction of variable AGN in these magnitude matched samples. And the takeaway here is that for galaxies between 10 to the 9 and 10 to the 10 solar masses, I find the same fraction of variability selected AGN as in the higher mass galaxies above 10 to the 10 solar masses. So there's no difference in the variable AGN fractions for galaxies from 10 to the 9 to 10 to the 10 and above 10 to the 10. There does seem to be a much lower number of them in the lowest mass galaxies, so below 10 to the 9 solar masses, which could reflect a drop in the occupation fraction, but could also be because it's more difficult to detect black holes in those tiniest galaxies. Okay, so I'll stop there. But if you want to talk to me about relations between black hole mass and variability properties, I will be around for the rest of the day. Just to summarize, active galactic nuclei in dwarf galaxies do exist and can teach us about black hole formation and growth. Finding them is really difficult, but I found that optical photometric variability can be a way to find AGNs in low-mass galaxies that are missed by other techniques, and there's lots of multi-wavelength follow-up observations of these galaxies underway. Thank you.
Thank you for this very nice talk, and more questions?
Sorry for going over.
So the interesting question is, why is there this 1%? And one possibility is that's the rush of the Eddington time to the age of the universe, the time that black holes are expected to be active before they feed back and remove the gas.
Right,
So,
you mean the duty cycle?
yeah,
Yeah.
but it's an interesting number. You find more or less constant, and the Eddington time is universal,
Right.
irrespective of black hole mass. The age of the universe is universal, so it might be related.
How contaminated do you think you are by supernovae?
Not at all. I mean, we do find supernovae in our sample, but they don't have light curves that are well described by a damned random walk. And anything that is variable is inspected very carefully by me. So anything that did get through that looked bursty would be, taken out. And of course, there could also be tidal disruption events. And so there's interesting stuff to be found in the bursty sample, but they are not contaminating the AGN.
If there were offset ones, would you have caught those?
Not necessarily. So I look at the nucleus magnitude here is measured in a 3 arcsecond aperture that is centered on the center as defined by the NASA Sloan Atlas. So generally that's the brightest point in the galaxy, and so like the example I showed before, this is the thing that's variable, and that's what's defined as the center in the NASA Sloan Atlas. So in the sense that the brightest point is what's usually defined as the center, then you can find off-center things, but yeah, it's something that I've thought about a bit. I do measure the full galaxy luminosity, but if there were something very faint, it could be drowned out by the rest of the galaxy.
Yeah, am I right to draw the conclusion from your talk that in order for you to have enough broadening of lines, you really require very strong gravity? That's why you only get it for supermassive radiance, which are huge, and once you go below a certain level, you get less broadening. Is that
the broad emission lines that you usually detect in AGN? Yeah. So the width of the broad emission line is directly related to the black hole mass. So,
right, so
the more massive black holes will generate broader emission lines, but whether or not you see them is thought to be, for AGN, more of an effect of the angle that you're viewing the galaxy at. So generally, it is thought that AGN have a structure where you have this broad line region close to the black hole where the gas is nearby enough for its motion to be dominated by the gravity of the black hole, and then there's some kind of obscuring torus around it, and so depending on the angle that you view the galaxy at, you may or may not see into the broadline region. So whether or not you see the broad lines from an AGN is thought to be more of an inclination thing.
Right, so there's always a broad region close enough to any black hole because gravity is strong enough.
Yeah, exactly.
Anywhere near the black hole,
Yeah. The luminosities would be fainter for smaller black holes, so you might not detect them for that reason, but it would still be, broad emission would still be generated.
Yeah, I have a very quick question. Have you found any of these intermediate mass black holes that are completely off the M signal direction? Because I remember that your 50,000 was fully on top of it.
Yeah, I haven't found any that are completely off, and actually I just took some new observations a couple of weeks ago, so I should have an updated M sigma paper soon. But they all seem to agree with the extrapolation of M sigma to low masses. Yeah.
More questions? So, yeah.
Want to say some words about all the multi-wavelength follow-up?
Oh, sure. So I will be getting VLA observations soon of some of the galaxies from the Stripe 82 sample that have AGN-like variability and star formation dominated narrow line ratios. We've also been doing higher resolution spectroscopic follow-up to see if when you can isolate the nucleus better, then the narrow emission line ratios change. And we do find that that's the case for some of the objects, that if you can really isolate the emission from around the nucleus, then the line ratios do become AGN-like. Hopefully there will be X-ray follow-up in the future, which would be great.
Yeah, so let's talk both of our speakers again.